Hello everyone. In this video, I'll talk about read-only memories used in digital circuit designs. Let's start by understanding the basics of computer memory. The memory in computers is primarily classified into two types: RAM, random access memory, and ROM, read-only memory. RAM allows both read and write operations, but it is volatile, meaning that its data is lost when the power is turned off. ROM, on the other hand, is non-volatile and can only be read from, making it ideal for storing fixed data or predefined logic essential for system functionality. In this discussion, we'll focus on ROM, its application, types, and how it works in digital systems. ROMs are widely used in various applications, including implementing truth tables, as any logic function can be realized using ROMs. Storing the BIOS, basic input-output systems, which contain boot instructions and firmware for hardware devices, which retain data when power is removed. It is also used to store lookup tables and implement finite state machines in digital circuits. These applications highlight the importance of ROM in modern computing. Now let's look at different types of ROMs. There are several types of ROM, each designed for specific use cases. Here is a quick overview. PROM or programmable ROM. This can be programmed once using a special device but cannot be erased or rewritten. EPROM, that is erasable programmable ROM. These ROMs can be erased using UV light and can be reprogrammed multiple times. Electrically erasable PROMs. These ROMs can be erased and rewritten electrically without requiring UV light, offering greater flexibility. Flash memory or flash ROMs, a faster and more efficient version of electrically erasable PROMs, which allow data to be erased and rewritten in blocks. This is commonly used in USB drives, SSDs, and firmware storage. Additionally, there is one more type of ROM which is programmed during manufacturing. It is called masked ROM. In this, the data is permanently written during manufacturing and cannot be modified afterward. Each type of ROM has its unique advantages, making ROMs suitable for a wide range of applications. To understand ROM better, let's examine its high-level block diagram. ROMs typically have n input bits, which determine the number of accessible memory locations. With n input bits, a ROM can access 2 to the power n address or locations in the memory. Each address stores a word that is m bits wide. The total memory output is m bits per read operation. Let's consider an example. Here, the ROM has 3 input bits. This allows addressing 2 to the power 3 or 8 memory locations in ROM. If each location stores 6 bits, the total storage capacity for this ROM is 48 bits or 6 bytes. Now let's review some basic definitions of a ROM array. We will first talk about a NOR-based ROM array. A ROM array consists of columns and rows. Each column is called a bit line and each row is called a word line. For example, in the ROM array shown here, there are 4 word lines, WL0 to WL3, and 4-bit lines BL0 to BL3. Since this ROM has 4 word lines and 4-bit lines, this can store a total of 16 bits of data. Now let's talk about the cells in the ROM array. The intersection of each row and column forms a cell. In this ROM, you can see multiple cells such as this one and this one. If you look closely, there are 2 types of cells: a cell with an NMOS transistor in it and a cell without an NMOS transistor in it. The presence and absence of the NMOS transistor determines the value stored in the cell. The cells with an NMOS store a logic 0 and cells with no NMOS store a logic 1. For simplicity, we can say that a 0 or a 1 in the ROM array is distinguished by the presence or absence of the NMOS transistor. This simple distinction allows ROMs to store and retrieve data efficiently. Now, after understanding the basic definition, let's address an important question: why this ROM array is called a NOR ROM array. If we look closely, each column in the ROM array effectively functions like a NOR gate. An efficient implementation of a NOR gate is achieved using dynamic logic, which is preferred to create fast and efficient logic gates. Let's explore this further. Here is the circuit of a 3-input NOR gate implemented in dynamic logic. If we compare each column of this array, we can see that it resembles the NOR gate in dynamic logic. In this design, the output node voltage relies on the parasitic capacitances to store the logic value. The pull-down network is designed like a regular CMOS NOR logic gate. The pull-up network is different. It uses a single PMOS transistor with a clock signal at the gate. This combination allows for efficient and high-speed operation. This dynamic logic gate operates in two phases. Pre-charge phase, where the clock signal is 0 and the output node is pre-charged up to VDD. After pre-charge phase, the design goes to evaluation phase, where the clock signal goes to 1 and the pull-down network comes into play. If any of the transistors in the pull-down network is on, the output node transitions to 0. And if the pull-down network is off, the output retains its previous state. This two-phase operation ensures fast and reliable logic evaluation, making it ideal for NOR ROM arrays. Now let's understand how the read operation works in a ROM. We will discuss the NOR ROM array that stores a specific set of predefined values shown here in the truth table. A ROM circuit begins with a row decoder, which takes in n input bits and generates 2 to the power n output bits. These output bits function as the word lines, enabling access to 2 to the power n words in ROM array. In this example, the row decoder has two inputs A and B, which generate 4 word lines WL0, WL1, WL2, and WL3, which are the word lines for the ROM. Before any of the word lines are activated, the PMOS transistors in the ROM array are pre-charged. During this phase, the clock signal, denoted as phi, is 0, and the output nodes Vout0 to Vout3 all are pre-charged to VDD. During pre-charge phase, all word lines are at 0. Once phi or clock signal transitions to 1, the dynamic NOR gates enter the evaluation phase. In evaluation phase, one of the word lines are activated. Suppose the word line 1 gets activated and there is a logic 1 at it, while all other word lines still remain at 0. With word line 1 at logic 1, the NMOS transistor connected at the intersection of word line 1 and bit line 3 turns on. At this point, the node Vout3, which is pre-charged to VDD, is pulled down to 0 or logic low. As a result, the value on bit line 3 becomes 0. Similarly, for bit line 0, the NMOS connected to word line 1 also has a logic 1 at its gate, pulling the value of Vout0 to logic 0. This sets bit line 0 to logic 0. On the other hand, the bit lines 1 and 2 sample the value at Vout1 and Vout2 respectively, which remain pre-charged to VDD. As a result, the bit line 1 and bit line 2 are at logic 1. These bit lines then pass through inverters, producing the output bits Out3 to Out0 as 1, 0, 0, 1. This corresponds to the second word stored in the ROM, which is the final output of the read operation. Similar to a NOR ROM, a truth table can also be stored in a NAND ROM, where the pull-down network of a dynamic NAND gate in the columns resemble the pull-down network of a CMOS NAND gate. However, there are key differences in their properties. In this NAND ROM implementation, the same truth table discussed earlier for a NOR ROM is used. Wherever there is a logic 1 in the truth table, an NMOS transistor is placed in the cell. The voltage value at the top of the bit line, indicated here by the green dot, is checked to determine the output. During the pre-charge phase, all capacitances are charged up to VDD and all the bit lines are at VDD. In the NAND ROM, the row decoder is active low. This means that the row decoder activates the row by putting a 0 on the word line, while all other word lines remain at 1. For example, suppose we are reading from word line 2, which is set at 0. The other word lines 0, 1, and 3 remain at logic 1. As a result, the bit lines 1 and 3 remain open and their voltages stay at logic 1, while bit lines 0 and 2 are pulled down to logic 0. This results in the sequence 1, 0, 1, 0 being read from the ROM. After understanding the read operation from a NOR ROM and NAND ROM, let's discuss how do they compare. NAND ROM is generally slower than NOR ROM because the NMOS transistors are connected in series, which increases the resistance and delay in the pull-down network. The read operation involves discharging the bit line through multiple transistors, which takes more time. On the other hand, NOR ROMs are well known for their high speed. These have fast read access time because each bit cell is directly connected to bit line, allowing for a parallel evaluation, which makes them suitable for applications requiring high-speed access. In contrast, NAND ROMs offer higher density compared to NOR ROM because the NAND configuration requires fewer transistors per bit. The series connection allows more bits to be stored in a smaller area, making it more compact. This is why the majority of mass storage devices today, such as SSDs and USBs, use NAND flash memory. In NOR ROM, during a read operation, multiple bit lines may be activated simultaneously and discharged to ground. This parallel discharge leads to higher current flow and increased power consumption. In contrast, in a NAND ROM, bit cells are connected in series along the bit line. This series connection reduces the number of active paths, resulting in lower current flow and reduced power consumption. So this was all for this video. I hope this explanation helps you to understand the ROM circuit better.